I'll start introducing our guest lecturer today, Professor Matthew McCabe. He's a professor of remote sensing and water security at the King Abdullah University of Science and Technology, or KAUST, in Saudi Arabia. And he received his PhD in civil and environmental engineering from the University of Newcastle in Australia, and held postdoctoral positions at Princeton University and the Los Alamos National Laboratory. Before he moved to KAUST in 2012, he was also associate professor at the University of New South Wales in Australia. We had a nice exchange with Matthew about a month ago when he was still in France. Now he's back to Saudi Arabia, and talked about his broad range of research interests. He's essentially exploring really a broad range of multidisciplinary challenges around food security, climate change, impacts, and precision agriculture and water resource monitoring in particular. So water-food nexus is a special interest. He has a particular interest in the use of novel technologies for enhanced Earth observation and data model integration. This includes, for example, CubeSats and unmanned aerial vehicles, UAVs, which we all learn more about in our phenology program, and in situ monitoring techniques as well to monitor terrestrial processes that could inform then models and statistics for the analysis of systems behavior. He has published 170 or more papers by now, and is one of Clarivate's highly cited researchers. And we are really grateful, Matthew, for the fact that you made time for us today. In order to have a professional discussion afterwards, I have passed the moderating responsibilities to Dr. Olena Dubovic, who is the scientific coordinator of our Center for Remote Sensing and Land Surfaces. So after your 35 minutes talks, we will have at least 45 minutes time for discussion moderated by Olena. But now I'm done, and the floor is yours, Matthew. Looking forward to your talk.
Yeah, thanks, Jan, and thanks, Joachim and Elena for the lovely invitation. Hannah as well for organising this and the communication that we've had over the last month or so. So it's really a great pleasure to be invited to deliver this talk and what's been a really interesting series on these innovation pathways to sustainability. I know that this is not an ideal forum for such presentations. We were just talking about some of the positives and negatives of these Zoom presentations. But I've really been enjoying many of the previous talks, albeit remotely, and their exploration of quite diverse aspects of this sustainability challenge. Now, from my discussions with Jan and Joachim previously, I understand that this is a multidisciplinary audience, and for me that's great because I do lots of different things. And I'm also going to talk about a multidisciplinary problem. So I'm really excited about the discussions that we might be able to have at the end of this presentation. So while I'm going to explore some aspects that are specific to my own areas of research, and Jan mentioned some of those, CubeSats and UAVs, I'm going to talk about many others. I'm not going to go into the deep specifics. I'm deliberately trying to avoid some of those to keep it general. But obviously, I'm more than happy to go into an exploration of those after the talk. Now, given that I'm doing this remotely, it'll probably be too hard to adjudicate any questions during the talk, so I assume we'll just keep those towards the end of the seminar. I expect there's going to be plenty of time, but Elena, if I look like I'm going over time limit, just give me a heads up and I'll wrap it up as quickly as possible. So today I'm going to talk about data-driven agriculture. What that might look like and how it might answer some of the big questions that face humanity. The United Nations has projected that somewhere between 9 and 10 billion people will inhabit the Earth by 2050. That's basically an extra 2 billion people over the next 30 years. Now, while there are some nuances to this number, what is agreed upon is that the majority of these 2 billion people are going to be born into the developing world. And they're going to be born into a world that's likely to be even more challenging to live in than it already is. So to meet the food demands of this growing population, some estimates suggest that we'll need to double our food production from current levels or 2005 levels. Now, this is a pretty daunting prospect, 2 billion extra mouths to feed in 30 years. But there's one thing we often miss when talking about future food security, and that is that we're actually dealing with some of these problems now. So while we can argue whether it's 50% or 70% or a doubling of food production, this is not really just some problem for the future. Today, there's more than 800 million people that are undernourished, and about the same number lack access to safe drinking water. So this is not just a problem of our age, it's a problem of our time. So articulating problem is always a good way to start a presentation, and this particular one is quite a big one. How will we achieve food and water security? Now, I combine food and water because the two are really inextricably linked. Approximately 70% of extracted fresh water goes towards the production of our food. You simply cannot have food security without first achieving water security. Now, if I wanted to further complicate this discussion, and I'm not going to, but I could add energy into the mix. Agriculture is second only to energy production in terms of greenhouse gas emissions. And on top of that, when we consider climate, which is really a threat multiplier in this food, water, and energy nexus, it becomes a very tangled web of challenges. But it's really one that we have no alternative but to address. Now, any solution that we arrive at will need to try and satisfy these core principles of sustainability. And I could spend the next hour or more talking about nothing other than the challenges of achieving sustainability, especially when it comes to reconciling the social, economic, and environmental impacts. But I'm absolutely sure that there are others in your audience and elsewhere that have far more knowledge than I do on this particular topic. And since there's no way I could do it justice in the next 30 minutes, I'm going to cheat a little bit and focus on just one element of this sustainability triad, and that's the environmental impact. And specifically, how Earth observation data may help us address and ultimately answer aspects of this food and water security challenge. Now, Jay Fimiglietti, Matt Rodell, and others have provided some really great insights into global water declines using the Gravity Recovery and Climate Experiment, the GRACE satellite. Now, one of the trends that has emerged from this data was a very strong overlap between irrigated lands, which incidentally was work that the University of Bonn led the world in mapping some years ago, and groundwater depletion. Now, to cut a long story short, we're using our groundwater resources much faster than they can be replenished, particularly in irrigated regions, which quite clearly has major implications for food security going forward. Now, irrigated lands make up around 20% of all farmland, but produce more than 40% of our food. It's really an outsized contribution. And they're particularly important in developing countries where they provide a strong lever on food security. Farms that have irrigation are better able to manage variabilities in hydroclimatic variables, rainfall, than those that don't. Now, there was an FAO report from around the turn of the century that estimated that up to half or even 2/3 of future crop production gains are expected to come from irrigated lands. So the solution to food security seems pretty simple, right? More irrigated lands. But obviously this is not a straightforward answer. There are lots of challenges with irrigation, not only the economic and logistical considerations, but also the environmental concerns. Now, there's a study by Carol Dalen, Michael Puma, and others that provide a really nice illustration. This is a 2017 study. They found that around 10% of groundwater depletion is embedded in global food trade via roughly 20% of global crop production that's traded internationally between countries. Now, the work has its origin in the virtual water concept, which I'm sure you're all familiar with, but uses that to explicitly track the groundwater exchanges in our international food systems. Now, the figure on the left, which is from a different publication, shows that Europe is one of the biggest importers of virtual water. The figure on the right, the one I want to draw your attention to now, goes into a bit more country-specific detail and focuses on some specific food crops. Now, I'm going to present a little bit of the detail because it tells an interesting story. So if you look at the numbers, they actually represent cubic kilometers of water, billions of cubic meters of water per year. And the colored ribbons around the periphery indicate the country of export. So, let's see, you consider Mexico, which is green, for instance, at the bottom, they're exporting about 1.5 cubic kilometers of depleted groundwater to the US. And the US is in turn exporting 1.17 cubic kilometers to China. Now, the top 10 importers, if you look at the periphery, the countries around there, the top 10 importers are bolded, and the top 10 exporters of groundwater depletion are underlined. Now, if you look at Saudi Arabia, which is on the left-hand side towards the bottom, it's bolded and underlined, which generally can't be a good thing. There are actually 5 countries in the Middle East that are among the top 10 importers of depleted groundwater per capita. So why does this matter? Well, it's a region that already imports a huge proportion of its food, around 90% in most cases. And now we can see that a significant proportion of that comes from farmland, international farmland, that relies on non-renewable and depleting groundwater. This is a real-life case study in food and water insecurity. So given where I live in the Middle East, in Saudi Arabia, this is obviously something that we've been trying to get more information on, particularly quantifying the water being used in food production and its subsequent effect on groundwater aquifers. And that's what you can see here. The top panel tracks the rapid expansion of agriculture in the last few decades, basically from nothing to the desert that it is, to a very intensive collection of irrigated farms. In this region alone, there's probably 4,000, 5,000 center pivot systems. Along the bottom, you can see the subsequent groundwater depletion from this region as a direct result. Now, when we started this work some years ago, I was really surprised at how much we didn't know. And some of that I'm going to talk about shortly. And we're only now just getting a handle on how much water is being used in food production in the kingdom. Now, one of the reasons for this is that for the most part, water use is not something that's actively measured, principally because it's not something that we really value. And I mean value both in terms of the importance that we place on it, but also as an actual currency. Water is a currency. In a system where water is largely free, where's the incentive to monitor and measure how much you use? So it's important to note that even though I'm using Saudi Arabia as an example here, this is not a Saudi-specific problem. Almost without exception, wherever there's groundwater-based irrigated agriculture, the groundwater systems are being depleted, often at alarming rates. And overall, we're doing a pretty poor job at measuring that accurately. This is where data-driven agriculture, the focus of this talk, and Earth observation, the 2 technologies I'm going to talk about in particular, can play an important role. So I think we all understand that feeding more people is not simply about growing more food. If we were to just focus on that, we could just consume more land, more water, more nutrients, more energy. Obviously, that's completely unsustainable. And of course, we're going to need to do all that anyway within a system that's already being impacted by climate changes. So in terms of solutions, there really is no single silver bullet. It's a multifaceted problem, a multidisciplinary problem that's going to require a multi-pronged approach. Now, the intent of this presentation is to explore just one possible approach towards addressing this challenge. I always like to say I can pose the question, I may not have the answer, but I may have a partial solution, and that's where we're going to be directing this this presentation towards. So as we all know, food production is the largest cause of global environmental change, with particular impact on our water resources and natural ecosystems. We've seen some examples of that already. Now, one of the most prominent approaches that's been proposed to address future food security is the concept of sustainable intensification. Now, to translate this complex topic into simple terms, and if you haven't already, I'd really encourage you to go and read the paper by Kasman and Grassini that came out recently this year. It really provides a great oversight of that. We want to produce more food for the same area without degrading the natural environment. At its heart, it has many parallels with, probably more familiar concept, precision agriculture, which is basically to do more with less. So I'm kind of linking the two here. Now, it's important to recognize that at the moment, we're not doing that at all. We're producing more food than ever before, but at the cost of more land, more water, more fertilizer, and more degradation. Now, if we're going to reverse this trend, we're going to have to be a lot smarter about how we produce our food. And if we're going to be smarter, we're going to have to develop new information sources that can give us insight into our agricultural systems. Now, for a sector that employs 1.3 billion people and represents a 2.4 trillion industry, agriculture is in many ways still stuck in the dark ages. In the terminology of Silicon Valley, it's an industry that's ripe for disruption. Now, if we're to address some of these major food and water security challenges, I really believe that we'll need a digital transformation. Now, just to be clear, this is not just about collecting more data. That's actually not all about collecting more data. We already collect more bits and bytes than ever before. It's something like 90% of the world's data was created in just the last 2 years, and that's a statistic that's been true for the last decade or more. I remember first seeing it 5 or 6 years ago. But while the absolute volume of data has increased dramatically, I'm not sure we're actually any smarter for it. Personally, I don't think we're properly harnessing the power of this data deluge. It's my contention, it's not just my contention, there's many others, that if we're going to support sustainable intensification, we need local level knowledge at the planetary scale. And that's a theme I'll be referring to quite a bit, local knowledge at the planetary scale. And I'll keep repeating it. So a few years ago, I wrote a forward-looking synthesis to identify some of the potential technologies that may reshape the field over the next 5 or 10 years. Now, the paper's titled, Future of Earth Observation and Hydrology, but it's not just hydrology focused. Don't let that dissuade you from checking it out. It's really the future of Earth observation, full stop. Now, one aspect we looked at was the effort by companies like Google and Facebook, who are employing stratospheric balloons in the case of Google, or solar airplanes, Facebook were exploring that, to bring the internet to the 2 billion people who don't already have it. It turns out they're mostly the same 2 billion people who struggle with food and water security. It's an untapped market for them, but it's an untapped market in more ways than one. But this concept of local knowledge at the planetary scale can actually benefit from some of these commercial efforts. Over the next few slides, next 15 minutes or so, I'd like to illustrate some of the emergent opportunities in Earth observation and how we can use these data, harness this data, to drive new insights. So 2 that I will touch on today, I've already mentioned, CubeSats and unmanned aerial vehicles. Now, on this slide, you can see the type of local detail that can be retrieved from these platforms. At the top, we have an image from a UAV. It's taken over a cornfield here in Saudi. You can see part of the center pivot boom, around 25 meters of that, but to put it in scale, these booms are probably 400 meters in radius, and they go around an 800 meter field. Now, when we put thermal imagery on them, you can actually see the spray. So it's some incredible imagery that you get from it. Wheel tracks, really plant to leaf scale observations. At the bottom, you have a panel of imagery from some common sensors you're probably all familiar with, and maybe some others that you're not. Now, till recently, and by recently I mean within the last 3 or 4 years, you really had to make a compromise between how often you could see something on one hand, daily in the case of MODIS, but at 1 kilometer resolution, and how well you could see it, 10 to 30 meters with Landsat or Sentinel, for instance. But you couldn't have it both ways. It was either resolution or repetition. Now, the game-changing aspect of CubeSats, which is what you see in the bottom right example, is their ability to collapse the spatial and temporal constraints. With 3-meter resolution every day, they've negated that spatio-temporal compromise. Now, the CubeSat concept, for those who aren't fully familiar with it, it's actually pretty simple. You know, instead of launching a single billion-dollar satellite, you launch many, a constellation of maybe hundreds of smaller, cheaper systems if you want to do it at scale. And what this enables is a shift not only in how detailed you can image the Earth, but also how often. Now, this has also opened up a new form of space-based investigation. Launching a satellite is not just the domain of ESA or NASA, European Space Agency or NASA. Anyone can do it. Space is becoming the new laboratory for Earth and environmental scientists to explore their own mission concepts. But they aren't problem-free. They do come with some of their own issues. This is, they're not the perfect solution, and I don't want to give that impression. I'm going to show you some of the issues very shortly. But because you have hundreds of individual satellites, you have hundreds of different sensor characteristics and sensitivities. And because they're cheaper, they're not necessarily the same research quality sensors that you might get from Sentinel or Landsat. You do get what you pay for. So there's an obvious difference between the sensors on a billion-dollar satellite versus the commercial off-the-shelf versions that are on CubeSats. And you can see some of these types of issues, one that we talk about in this short video I'm going to play shortly, where we'll see multiple different satellites collecting a region over South Africa in this example. Let me get this one started. So there's gaps. This is over a year, but you'll see gaps. There's variations in radiance. There's clouds. There's temporal adjustments as you go through. Lots of things to consider if you want to make informed decisions on the ground. So the first question we had to address was how to leverage, what is a really fantastic resource that, as I said, collapses these spatial temporal constraints. How do we leverage these many different observation systems to get research level data and metrics out of them? Because that's ultimately what we want to do. Now, to do that, we had to develop a harmonization approach to address those types of interoperability problems I just mentioned. I'm not going to go into the specifics. I've referenced the paper down there that you can refer to if you want to go into the detail of it. But basically, we developed a machine learning approach that fuses the best elements of spatial and temporal resolution and radiometric accuracy from the multiple different platforms we have available, whether it's MODIS, Landsat, Sentinel, and the Planet CubeSats. And by doing that, we can form a single harmonized product. Now, as I said, the work's described in the reference paper, but it's recently been operationalized by Planet, the owner and operator of these many hundreds of CubeSats, by one of my former research scientists, Rasmus Hoborg. And I want to thank Rasmus for providing some of the video content here, which I think gives a really graphic example and illustration of the novelty and benefit from these systems. So with this machine learning and data fusion approach in place, you can now get something like this. Let me play the video. A seamless, kind of harmonized and gap-free product. You can remove the clouds, allows you to start asking some of the research and operational type questions that we need with a lot more confidence. You turn something that is now a research quality operation. Now, the types of questions that will help to address some of the sustainable intensification issues that we need to answer around food and water security, they're the ones that we need to be able to adapt to these new information sources. Now, in the next few slides, I want to show you a few examples of the types of agricultural informatics that we've been developing from these data and potentially how they could be used. Now, in this example, we're tracking the greening up phase of an alfalfa crop every day using very simple NDVI, normalized difference vegetation index, to help identify any problems or issues that might be occurring in the field. Now, as a comparison, I've bookended the 8-day sequence of the CubeSat imagery with Landsat data at both ends, from day 206 to 213. Now, apart from not being able to resolve any of the fine scale in-field detail, the information the farmer would need to make informed decisions on the ground. The Landsat has a temporal resolution that completely misses important crop development stages. Now, for those that use Landsat, you'll know that the usual frequency is around 16 days, not 8 days. I'm not cheating here. We're just fortunate enough to have an overlapping swath at this particular site, which reduces the repeat rate down to around 8 days. At 16 days, and with the usual problems of cloud cover, you're really going to miss quite a lot of the information that you need to address operational on-the-ground type questions when you don't have daily resolution, daily retrieval information. Now you can expand the approach beyond NVI to develop much more detailed metrics. Such as in this case, we're using the leaf area index. Now you not only have insights into crop health and condition, but also phenology development, planting and harvesting times, key stages of development and maturity within the crop cycle, which is exactly the type of agricultural informatics that we need to make the type of informed decisions to deliver sustainable intensification. So I'll walk you through an example. Growth rates not only give you information to undertake yield forecasting if you were to merge them with a crop model, which is a key metric for food security, but you could also use the pattern of growth and planning to help you identify the type of crop being grown, which is fundamental in trying to understand our food and water security, our yield forecast activities. But something like what type of crop is being grown, let alone how much you might expect to yield, actually doesn't exist at the time and space scales required to make effective food security forecasts. But this is the information that we need. Local knowledge everywhere at the planetary scale. So once you have what I call level 0 and level 1 data, these basic agricultural informatics, you can start to develop higher level precision agricultural insights. In this case, and this is a couple of years old now, we've done some subsequent work on this. We produced estimates of crop water use, basically the evapotranspiration, at a resolution of 3 meters and daily, the highest resolution at that time and still ever retrieved from space. Now, knowing this has implications not just for agricultural water monitoring, but also water management. You now have a real basis for global licensing and compliance, putting an actual value on water. And to remind you, we typically do not know how much water is used to produce the food we eat, or where in the field to use more or less to maximize yield. And it's these type of data which are absolutely key to closing that so-called yield gap, the difference between what a crop could potentially yield versus what it actually yields. And that's a particularly important element in increasing food security in developing countries. Now, again, the ultimate goal here is local knowledge at the planetary scale, to measure and understand every field, everywhere, all the time. Now, when I first started in this area, I was actually really surprised by how much we didn't know about our agricultural systems. For example, something as simple as the number of fields in a country. That's a statistic that's really hard to find because in many places it just doesn't exist. Now, if you don't know something as simple as the number of fields, you don't know what crops are being grown, how much is being produced, how much water is being used to grow all that food. Again, things which you all fundamentally need to know to make any progress towards either food or water security. It's as simple as an old business maxim that I use in pretty much all my talks, and this one's not going to be any exception. You cannot manage what you do not measure. So while we are increasingly data rich in all fields, we remain information poor in many ways. Now, we recently completed the first phase of a government-funded project to map and monitor agricultural water use throughout the kingdom. And it involved mapping every unique center pivot field, and there's up to date about 35,000 of these spread around the kingdom over multiple years, determining the crop water use rates, and then inferring groundwater abstractions. Now, I'm not going to go into how we did that or the models. This paper kind of explains that. But as I showed in one of the earlier slides, agricultural production using groundwater is pretty much unsustainable in many parts of the world. But we're finally putting real numbers on this to help manage that better. You know, obviously the next phase is to expand beyond Saudi to everywhere else, to those regions in particular where the information is not readily available or doesn't exist, but is really desperately needed. But that's the power and potential of Earth observation and big data analytics. Now, the term I use to describe the type of data, this agricultural informatics, it sounds a lot more impressive perhaps than it probably is. You know, ultimately, it's really just about turning the data into useful and usable metrics. And importantly, getting it into the hands of people who can use it in a timely manner. And there's been a disconnect for many years in that regard, getting the information to where it's needed. Now, this is being driven by a range of platforms. It's not just satellites and UAVs, which I'll talk about shortly. It's also in situ sensors, in situ systems, wearables, on-plant, on-animal sensors, you know, the Internet of Things applied to Earth and environmental science. And this is really the forefront of sensing. And it's expanded, you know, dramatically, even in the time that I wrote that paper several years ago. There's things that we didn't capture that we just weren't aware of that have suddenly accelerated to provide us as new information sources. Yeah, but the real opportunity, and in many ways, I think the real challenge lies in that analytics side. You know, turning the data into decisions. Now, the power to develop information across the world can then be put into the hands of, you know, those who need it most. That's that missing gap that we need to bridge. Now, one of the more novel applications we've been exploring at CAUS developed through collaborations with plant scientists. And collaborations I probably wouldn't have made had I not come here, to be honest. And these guys undertake large-scale phenotyping studies in the field. You know, I say large scale, it's certainly not the large scale that we usually operate on in the fields in the kingdom or at global scale, but it's large scale when you consider you're going from a greenhouse to a field. But essentially, they're trying to identify favorable characteristics across, you know, very large numbers, several hundreds in cases, even thousands, of various plant accessions. Now, UAVs allow this to happen in a much more automated and controlled way, you know, really enhancing what's otherwise a traditional and laborious approach of the manual field-based sampling. Now, we've been doing this across a range of plant types and field conditions. You know, that's work that we've been publishing recently, delivering a, you know, quite a rich analysis of the plant response to both environmental change, or if you want to accelerate that, introduce stresses. And that's the advantage of these types of studies. You can introduce stress, whether it's through salt or holding back fresh water to inhibit a drought or express a drought. Now, to date, much of this is what I kind of term, you know, the first phase, the more straightforward analysis, where you link observable features from the UAV with field measurable variables in a traditional in situ sampling approach. And it's really not too dissimilar to what we do with space-based remote sensing platforms, but obviously just an order of magnitude improvement in resolution, and obviously with a subsequent increase in data volumes as well, which represents its own challenges. But it's really leaf to plant level assessment that you're getting at, not field scale. This is centimeters rather than meters. Now, I don't want to minimize the science here at all, because there's a lot of really interesting and novel science going on in this work behind the scenes, but, you know, straightforward's a relative term. And in many ways, we're still quite immature in using UAVs for high-level phenotyping studies, but, you know, we're really making great progress. And by we, I mean the community, not just our group. It's kind of one of those rare instances where the technology is not constraining the science. we can answer questions now that even a few years ago we could only speculate on. And that's very exciting for a scientist in this field to be able to be at this point in time. I think some of the previous talks have mentioned the golden age of remote sensing. Well, in this regard, it's absolutely true. But it's really the next stage that I think is the real frontier. And, I call this the hard part, or the harder part. And that's linking the phenotype, the observable features that we can get from a UAV or on-the-ground sensing, with the genotype, the essential structure of the plant. And this is where I confront the limits of my expertise, which might explain why I call it the hard part. But I rely on the world-leading collaborators at CAUS and elsewhere, who can explore the real value in this type of analysis. But I raise it because it's another good example of the agricultural digitization that is needed to realize these future gains. Whether it's identifying the optimal plant type for a particular environment, or the specific genes responsible for switching on a favorable trait. The bioinformatics aspect is what we refer to. It's a great example of the collaborations that are needed, the multidisciplinary collaboration needed between plant scientists, computational specialists, statisticians, and even humble engineers, all with a focus on addressing this major question of food and water security. So in the same way we've used technology to harness water for irrigation, deliver nutrients through fertilizers, and even capture the sun with indoor lighting in greenhouses, we have a real opportunity to harness data on an industrial scale. I've stated already that agriculture is an area that's information poor, but increasingly data rich. And with that comes a great opportunity for insights and improvement. Now, that's really the concept behind agricultural informatics, the effort to turn data into useful and actionable insights. Now, I really believe that this will be one of the pathways, and I want to make that clear, this is one of the pathways towards delivering upon the promise of sustainable intensification. And I understand, I certainly appreciate how it sounds very industrial and mechanistic, but I really see a digital transformation as being able to enable us to do more than just input and output optimization for precision agriculture, which is kind of what I focused on today. It could or should capture everything in between the farm and the fork, from where we grow it to where we eat it. Traceability of food supplies, fraud detection, origin certification, waste production. Obviously, that's a massive concern. We probably produce more food now than we actually need by 2050. So waste production and disposal. A blockchain for food and water. That is the opportunity that's presented by these new informatics. So if there is a concluding message, this is my last slide. If there's a concluding message for my presentation, it's probably this. We need a digital transformation now so that we can answer the 10 billion people question of the future. And with that, I'll be very happy to take any and all questions and hopefully have some lively discussion in the meantime.
Thank you, Professor McCabe, for this exciting lecture full of interesting examples. I'm happy to start this discussion, and I would like to encourage all the audience to participate in. You're very welcome either to raise your hand and speak up your question, or maybe you have comments via video, or another option would be to write your comments directly in the chat. So while you are still reflecting on Professor McCabe's lecture, let me please shortly recap the lecture on data-driven agriculture and new pathways towards sustainability. So Matthew started out with making us aware that food and water security is already a problem of our time, which will only exaggerate in the future, and how essentially Earth observation could help us to address this issue. He introduced us to the concept of data-driven agriculture and talked about one of the possible solutions for sustainable agricultural intensification, which is digital transformation, including the need of agricultural informatics. He showed us exciting examples on how we can use Earth observation for crop health mapping, groundwater mapping, and phenotyping, and others. And finally, he particularly highlighted the benefits of using artificial intelligence, data fusion, and different data from various multi-sensing data streams for those exciting applications in agriculture. So now I'm looking at people, and I hope there are coming some questions to Matthew. Well, while still people are thinking, I actually have a question to start and kick up the discussion. Matthew, all those examples that you showed to us, they're really fantastic. It's really cutting edge research, but it's also possible because you have this very nice field experiments full of different sensors and the possibility to access the data from UAV, Planet Lab. So this is normally information that for users all over the world is not that easily accessible. So my question is, what do you think, how scalable are those solutions that are developed in your lab to other parts of the world? Or what would be the preconditions for this scalability of those approaches?
Yeah, this is a great question, and I think it cuts across every research area that uses instrumentation or laboratory work. The ultimate goal is that we're focusing on the science, but very much on the applied aspects of that science. So the usability and the transferability of the techniques that we're employing is absolutely at the heart of the work that we're trying to do. But you need the high-level information, the validation, the field data collected at the appropriate resolutions to ensure that you're actually providing something useful. But the idea behind all of this ultimately is that you can develop an algorithm or an approach that you can then scale everywhere and places where you don't have the data. That's the principle behind, or principle and promise, I should say, behind remote sensing. Now, I think there's a lot more with your question that we could explore, whether we've been successful at that or not. I tend to lean on the side that we've probably been less successful at the transferability than we have been in developing nice approaches to do things. But I think we're realizing more and more, particularly with these tools that are becoming increasingly available, tools like the cloud, where we can do large scale analytics, where we can expand beyond a single field to a nation, to the globe. I think that that is forefront in people's minds now more than ever. We have to deliver usable and useful tools.
Yeah, exactly. We have some questions already. So Henrik is asking, what is the most useful data you are still missing at the moment?
Yeah, great question. All right, the most useful data. I tell you, I mentioned this in the slide. I haven't always done precision agriculture. I came from a global perspective previously, where we did remote sensing at global scales, and it's probably the only last 10 years or so that I've kind of drilled down to the field. And it kind of relates a little bit to Elena's question. We've got some fantastic instrumentation, but there's actually some really basic information that I've surprised we didn't have. And that was, things like how many fields there are in a kingdom, what type of, in a country, what type of crops that they're growing, when are they planted, when are they harvested, this kind of level zero information. Now, for the work that we did with the water use, which has consumed quite a significant portion of my time, this government project, where we wanted to be able to track at the field level water being used and then scale that to the nation to identify every individual field. What we really lack is the validation data of on-ground pumping, irrigated amounts of water. So if I had a box of wish lists, that would be one thing, that we actually had a range of monitoring stations or supplies, like we have with air temperature or radiation, that measure the amount of water put on a field. It's data that just doesn't exist at the locations and the resolutions that you need. I can count on one hand the number of inline flow meters in Saudi Arabia because I put them in. But when it gets back to this point of valuing the property, valuing water, we don't value water anywhere. We use it, it's free for the most part. The biggest expense for a farmer in this part of the world is fuel to drive the pump, to pump the water. You don't pay for the water. If we did put a value on water, I guarantee you we would see a much greater monitoring of that. And with that information, we could develop a whole range of different approaches to quantifying water use. So I guess it's not an exciting bit of instrumentation. I hope I haven't disappointed you. It's the basic information at scale, in space and time, that we don't have. We could have, we just don't have it.
Yeah. The second question is from Julian Schroner. He's asking, why will 2 billion more people in 2050 require a double food production?
Yeah, great question. Great question. And I'll preface this by saying, there is some discussion on whether it's 50% or whether it's a doubling. And there's even studies that say we're already producing enough food to feed an extra 2 billion people. It's just that we waste most of it. If we reduced our food waste from the 30 or 40% that it probably is now, we could help cover that. But the principal driver of that doubling of production is not just the extra 2 billion people, it's the changing demographic of our diets and the foods that we eat. So as people get richer, as developing nations get a middle class, and as the incomes rise in those countries, their diet tends to shift, and it shifts towards meat and dairy products rather than a reliance on cereal grains, which is a natural evolution in diet. But to produce those higher protein count foods, you need lots more grain. You need lots of grain to feed cattle. So that's a big driver of that doubling, or let's call it 50% or 70%, depends on the paper that you read it. It's still a dramatic increase over what we're currently producing.
Next question again from Henrik. He's asking, how precise are your leaf area index estimates from the air when real LIE is more than 2?
Yeah, this is a good question, and I can refer you to the papers that we've explored the LAI retrievals. If you go to Google Scholar, you'll see that, where we actually use that planet data to estimate LAI. We have ground validation data over within the field. This is the whole purpose of doing it at high resolution, so that we could look at within field variability. We have intensive monitoring zones, as you would when you're measuring LAI. But in corn or even alfalfa, LAI doesn't stay at 2. It goes from 2 to 4 to 5, and a little bit more sometimes. So you do see the development of that LAI trend over the growing cycle. But in this type of area, if I can get within 15% of a field measured value, I'm very happy. That's probably the type of accuracy that we're referring to with our LAI. Between 10 and 20%. If I can get that with an eddy covariance instrument, I'm very happy. Maybe I'm too easy to please, but I understand how difficult it is, and as you say, it's very challenging when LAI is low. But just keep in mind as well, and this is something that I've really appreciated more and more over time. There's real value in the absolute estimates of some of these variables that we're interested in, whether it's LAI or crop water use or some other metric of interest. but there's just as much value in the temporal change and the temporal development. And as scientists and engineers, we probably focus more on the absolute than on the relative. A change in something tells you a great deal about what's going on in a system. And I think that's an area that we're under exploiting. I used the example in this talk about just mapping the phenology of vegetation growth through time, how long it is, how long the time to peak is. That's all information that you can use to give you insight into, you know, what it is that's actually growing there.
Yeah, that's definitely the case. I recall our discussion from my times as postdoc at Crop Science Institute, how we can use remote sensing to enhance crop models. And that was exactly the main point, that we can see the dynamics with remote sensing and capture it much more compared to crop models, for example. And this also my question to you, Matthew. Do you work with crop models or any hydrological modeling in your group, or you maybe collaborate? And in which way do you use remote sensing data then in this modeling exercises?
Yeah, really. So if I understand it, it was, you know, do we use crop models or hydrological models to you know, the downstream side of our remote sensing observations? Is that right?
If you use it, if you use those models for which tasks do you use remote sensing to calibrate models or to validate the results, or another way around?
Yeah. So you know, the big area in my field, and I come from a hydrological background, is kind of data assimilation. You know, we've got a land surface model or a hydrological model, and you want to assimilate soil moisture. I have done that, and I did do that, you know, 10, 15 years ago. But, you know, lots of people do that. We've actually recently, in the last few years, started exploring crop models and how we can assimilate variables into crop modeling. Now, this is an area I hadn't really spent any great deal of time exploring before. As I said, I'm coming from a hydrological modeling background, but there's a lot of similarities. You know, it's just physics and numerics. So we have been exploring a couple of different crop models with some projects that we had funded here to look at the precision agricultural insights that you can gain by ingesting UAV or CubeSat type data into these models. So we're using the AppSim model. There's an aquacrop as a side project that we're trying to you know, really, this is not something that a lot of people are doing. You know, crop models tend to be run at the field scale. What we're trying to do is run them at the within field scale, at the resolution of the satellite data, whether it's 3 meters or 10 meters, and ingest things like you know, leaf area index, maybe soil moisture, if that's a variable of retrieval. And we actually have some papers coming out on that shortly. We also go into some of the mechanistic processes of those models, how to improve the uncertainty in parameterizations, either through assimilation or through Bayesian type approaches. It's interesting coming from a land surface hydrology modeling perspective into a new community of modeling, the crop modeling community. You know, I'm still learning a lot in that area, but for me, it really is an obvious path on taking the types of observations and metrics that we're able to retrieve from remote sensing data and ingest them, you know, whether it's through assimilation or some other merging approach or fusion approach into these crop modeling type systems.
Exciting. Lucas is asking, do all of planet's CubeSat only carry optical sensors? If so, are there any plans to set up similar systems or satellite fleets for SAR sensors?
Right, yeah, excellent. So Planet originally just started with RGB, red, green, blue, on their first doves, and then they added a near infrared band, which was great. So the very first paper that we did with the CubeSats was just using RGB and then relating that to an NDVI, and produced some nice works. But as soon as they put the near infrared band on it, that was great. Now they've got super doves. They're 8-band. Within the visible near infrared range, but yeah, it's mainly optical. There are other companies and individuals exploring other approaches. I'm trying to think of any nano-SAR? I don't think so. The Spire is a company that does GNSS, global navigation satellite system reflectometry, which you can use to infer atmospheric processes and also soil moisture. We've actually got a project where we're trying to use GNSS for vegetation biomass retrieval at a sort of, again, as a useful information metric for the types of crop modeling I was talking about before. There's efforts, I think, to put a thermal system on, a sounding system, but you've got to remember the CubeSat concept, they're only shoebox-sized systems, and there's only so much you can put on board those. And also, there's power requirements, particularly with SAR, that you probably wouldn't get on at least a smaller CubeSat system. But I really think the opportunities to merge beyond just optical systems are there, and we're going to see more and more of those develop over the coming years as it becomes cheaper to get things into space. And again, the opportunities to do these kind of experimental sensing systems.
The question is related to this, so I will read it now. Hi, Mike, how do you treat the different generations of PlanetScope satellites with their different spectral response functions? Solely via artificial intelligence, or do you apply also physical models?
Yeah, so you can find out exactly about that in the CESTM model, because we take an approach where we're looking to fuse all across those different sensors, and they all have their own sensor characteristics. But at the end of the day, we're kind of training it to the research grade satellites of Sentinel and Landsat. So we don't explicitly account for physical differences by using radiative transfer modeling or anything like that. It's really a machine learning based approach. But that issue is one of the key aspects of the CESTM CubeSat enabled spatio-temporal enhancement method is the acronym. But that's certainly described in the paper, and it's going to be a bigger issue or a bigger aspect of the new SuperDove approaches, because they're going to have 8 bands. But again, since those first CubeSats were launched, the radiometrics and the accuracy on those systems have improved. And it's not like we have to do a 10-year synthesis where you have sensor degradation. These CubeSats only last for a few years at a time anyway. So you're often dealing with new and improved versions of the previous systems. It's a very much a software modeling type approach. Every time there's a new launch, there's a more mature optic systems often on these CubeSats.
There are 2 more questions on water. So Ken is asking, do you think that privatization of water supply could help in terms of acquire the missing data, such as the amount of water used in fields? Wouldn't this case cause a lot of other issues instead?
This is a really good question, and it's a question that there have been books written on. Is water a private or a public good? And I'm certainly not going to be able to do that argument justice. My inclination is that privatization of water supply has some benefits, but it also has drawbacks. And just as infrastructure is one of the big ones where private companies aren't going to come in and spend the billions and billions of dollars that are required to develop a water system. Now, I guess if you want a real world example of that, there are many papers that have sort of illustrated the benefits of irrigated agriculture in sub-Saharan Africa to meet some of the food security challenges. But what private company in the world is going to go in and invest in the ground infrastructure that's needed for the development of an irrigation system like that at scale? So I hazard to even jump into this debate, but it's a really good question, and I'm going to say that there are much smarter minds than myself that have provided much thoughtful answers, or much more thoughtful answers than I can give in the next 2 minutes. But really great question. It's actually a topic that we have. I have run a sustainability course here with the master's students, and that's a topic that we often explore and have a debate on. Water is a private or public good. But yeah, good question. I'm sorry I can't answer it.
Water and possible solutions. So Julian is asking, how about the usage of desalinated water from solar-powered desalination plants? Given that there is enough economic interest to establish these plants, could this be a sustainable solution to water shortages and irrigation, at least for coastal countries?
Yes, hopefully, but we're quite a ways off that. There's limited examples of sustainable solar desalination plants running agricultural facilities, and there's one example I can think of. It's in Australia, in South Australia, Sundrop Farms. If you want to go look at it, they use concentrated solar power, basically reflecting mirrors into a central vessel of water which they boil and steam to run a turbine, and they use that to produce high value crops. Okay, so tomatoes in that example. So there are examples of concentrated solar power to deliver some agricultural products. But for the types of water volumes that you need for cereal crops, I just don't see that it's feasible. You could certainly have greenhouse-driven sustainable systems for high-value crops, but you're not going to feed the world on cherry tomatoes and arugula. If growing wheat and barley and maize, and you need rice, you need large-scale areas, and the volumes that you're going to be able to extract from solar power aren't up to that. Desalination has its own problems, of course. You don't just desalinate water and that's the end of it. You've got a waste product. You've got highly concentrated brine. For every metric ton of water, you've got 30 kilograms of salt. So what do you do with that? And sustainability, the life cycle assessment of solar as well has its own challenges. You have storage for power, you have degrading solar panels over 5 or 10 years. But we're doing work. I'm the Associate Director of the Water Desalination Centre at KAUST, and even though I don't do solid desalination or desalination per se, I know enough to be dangerous on it. And we have some researchers investigating precisely this aspect, the combination of solar and agriculture. But do I see it as a solution to the global food security? Probably not.
Yeah, the last question is from Jan, and we are back to remote sensing for agriculture topic. So he's asking, how far are we from being able to derive eco-efficiency estimates from remote sensing data? For example, water use per kilogram of product, and what are the barriers to upscaling such estimates?
Yeah, this is a good one, and maybe you've read the Kastman and Grassini paper, because this is one of the things that they do highlight. What are the gaps in our observation systems and agricultural informatics, and this is the key one, or this is a key one. How far are we away from it? We could do some of these things now. It's how accurate they are is one challenge there. But if you want to look at water use efficiency in cropping systems, if we can estimate yield from our crop models with reasonable accuracy, 10 to 20%, as I said, that's the gold standard for me for most anything. If I can get to within 10 to 20% of the real answer, I'm pretty happy. So if we have our water use, if we have our carbon uptake, if we have our yield, you can get some of the water use efficiency type metrics that would be informative to assessing the sustainability of these processes. So I think there's going to be a lot more focus and emphasis, and this goes back to our pre-recorded discussion on the G20 initiative and the circular carbon economy. There's going to be a lot of focus on accounting. You know, I'm a glorified accountant in some ways. I take pride in the fact that that's kind of what we do. We try and account for water, for nutrients, for carbon increasingly. It wasn't something that I have actively focused on previously, but over the next few years, carbon accounting, particularly in agricultural and natural systems, is going to be very important. And I think remote sensing and some of our in situ sensing approaches are going to play a key role in doing that. Now, there's already been some great work that is attempting to bridge this gap. You know, I'm not doing this in isolation, but to draw a circle back to the original question, you are absolutely right. These are the types of metrics that we need to develop that can illustrate whether the systems that we have in place or the systems that we're proposing are suitable and sustainable for, you know, that sustainability triad, the economic, social, and environmental concerns. So, you know, to be advised, I think, is the short answer. But we're getting there.
So this is the last call for the questions to Matthew. Before we, I'm looking at the chat. I don't see the hands, but maybe a few minutes to give a few minutes to the audience to think about. I have a last question from my side. Matthew.
There's one raised hand by Hannah Kuhlmann.
Oh, sorry. Yeah. Please.
Yeah. Okay. Thanks, Matthew. I have a question to your one of your methods you showed us, especially to the fusion of your different CubeSat data and Landsat and models with your machine learning approach. My first question is it a pure data-driven approach, or are there some background models? For instance, you know that the desert always has to look in the same fashion, or do you have any plant growth models behind, or is it pure data-driven?
Yeah, it's pure data-driven. For the fusion, it's just relying on the satellite data. There's no physical growth models or anything going on behind the scenes.
Okay,
and that's a pretty simple sort of machine learning approach as well. Rasmus has probably made it more rigorous since our approach, but it was basically a cubist regression type approach. So the analysis-ready product that Planet develops, it may be actually more rigorous than our first forays into that.
Okay, and can you probably give me a little bit more idea, how did you do it? How many training data did you use, and where get you these data from, and how did you manage that? Or did you define a reference satellite which is most closer to your visual impression at least, or how did you do that?
Yeah, so that's it. It's the reference satellites, and this if you want to highlight an issue with the CubeSats, is that if you want to turn them into research grade sensors, you need a research grade sensor. Okay, and that's what we use with Sentinel and Landsat, or any other system that you wanted to merge. You couldn't do that fusion approach without the high quality sensors in the first place. So, to really simplify it, all we're doing is turning poor quality sensors or poorer quality sensors on the CubeSats and training them to the higher quality sensors on Sentinel and Landsat, and we use Modus for the temporal extrapolations. So without those systems, they're the training data, essentially, if you want to put it into those terms. The high quality space agency based systems are the ones that we train our CubeSats to.
Okay, and the last question to that is, I mean, obviously you bridged some scales. Yes, you had these 3 meter resolutions and these 1 kilometer resolution. And does this mean that this approach is in general possible to virtual scales. Probably I can explain my background for that. Within our cluster of excellence, we are collecting data from UAVs and from ground vehicle with a spatial resolution of some square millimeters. And at the same time, we have some satellite, images from the satellite with, with tens of meters resolution. And obviously it's not easy to bridge the scales between these.
Yeah, well, I think we need to talk offline because I don't want to give too many secrets away. But that is an active area of research that we're doing, is trying to take the CSTM framework where we go from 3 meters, we scale it up to 30 meters or even scale it up to 500 meters when we're looking at motors, develop the relationships and then scale them back down.
Okay.
It's not rocket science, but it had a fantastic result. You can see some of the results. They're really cool, but it's a natural progression then to do that with UAVs. So we're actually doing that now, taking the CSTM approach and exploring it from the UAV concept. So looking at it from two sides, can we use, it's all recorded now. So, if you get and do this before me, you'll have to cite me in some way. But basically we want to use the UAVs in two ways. Can we train the UAVs to the satellite data? All right, so we get over the calibration problems of UAV field. That's a big problem, right?
Yeah.
You want to go somewhere random, or if you want every farmer to have an autonomous system, they can't go and do the calibrations that we do for our field level retrievals. And the other way is, can we use the UAVs, the high quality UAV retrievals, to improve the training of the satellite data? So do time coincident fusion between planet and UAVs, but also UAVs and planet. But I've learned in my time that ideas are cheap. They're rare but cheap. Someone's got to go and do this work. So if it's a race to the finish, I reckon we should join forces and discuss this some more.
Okay. Okay, thanks.
Okay, thank you so much. So I guess if there is no burning questions from anyone, or if there are still some, I think you can reach out to Professor McCabe also via email further on, or bring it into offline mode, any other means of communication. And with this, I would like to hand over back to Jan.
Yeah, thank you very much, Elena. Thanks, Matthew. I think I take away a lot of interesting impressions. The one sentence that fascinated me most was, I think, to your last slide on what this means for, thinking from farm to fork, and the idea of managing the whole value chain. And that's, of course, a whole new world. I've witnessed this in the last 1-2 years, what an influence it can make when new papers come out that trace back impacts of commodities to their origin, globally traded commodities to their origin. I mean, we are now at the point where we can basically measure how much illegal deforestation goes into a ton of soy. But imagine what we can do when we can measure how much water and how much nutrients went into that kilo of soy, and what perhaps the social impacts were of expanding the soy on previously used public land. So I think that's really an exciting field of research where remote sensing and many other fields come together, and where I hope we can maybe talk about, especially after you and Heiner have clarified the scaling issues. We might come to the other things and discuss them as well, and maybe even get to some collaboration on those topics. Joachim, any final words?
Extremely interesting. At some point, we need to map where industry and where consumers are and connect them to the fields in order to really have the spatial dimensions of the value chains, and not only plants and crops and fields.
Yeah, I think this is, it worries me a little bit of how much I don't know. I think it's really an exciting time for any young researcher and PhD student or postdoc to get into this field. There's just so much opportunity, not only in the academic side, but in the private sector as well. But I'm constantly hitting my head against my lack of knowledge in these areas. It's trying to bring the different threads together. That's really the great challenge, I think. And hopefully I see many faces within the audience. There's some smart minds that can see these links and make them. And I think over the next few years, we're going to see some quite interesting and rapid advancements in these types of interdisciplinary questions.
You added a lot of knowledge today, at least to me.
Well, I look forward to the conversations.
Great. Thanks, everyone, for being with us. Special thanks to Matthew and Olena. And, we'll be in touch.
Lovely. All right. Thanks, everyone.
Bye-bye.